All right, thank you. What I am going to do, since I'm going to try to right the ship in terms of time, what that means is that we have a lot to go over and not nearly enough time. So let's get that started. So Swift does have first class closures, so you can use closures as types, pass them around. You can have higher order functions, return a function, accept a function to change things. I realized, even though we did just finish the category theory thing, how many people know what a higher order function is? Some people didn't raise their hand, which means, so a higher order function is basically a function that can accept some other function to do its work, or can return some function that it has created. Right? Unfortunately, I don't really have time to explain functions and what they are, but it's turtles all the way down. All right. Let's actually start with, since a few people at LambdaConf mentioned some things. There is a thing called CryptoPals, and they have an interesting challenge. You're supposed to create something that can turn a hex string into base 64 and do the other way. Right? And it turns out, I believe, base 64 to hex string, kind of trivial if you know the libraries and whatnot, not so bad. Hex string to base 64 baffled me, mostly because I had absolutely no idea what a hex string was. So a hex string, as it turns out, each of these two characters, or every two characters, is, I believe, a byte, and it's encoded in base 16, and you're basically just trying to turn this into like a string. Oh, I used to have this translated, which was something like, "I'll melt your brain. I'm melting your brain like mushrooms," or something like that. Like that's what the string said. In fact, I can probably just Safari. Hex string converter. This was very handy, which is to say the internet, because again, I had absolutely no idea what a hex string was at first. I'm killing your brain like a poisonous mushroom. That's the string. And so eventually, after I stared at this for a little while and then copied the first two characters, I was like, I get it. So then I had to figure out what to do. And because this was code just in response to someone else's question, I decided to go with what is now the natural way for me to write Swift code, which is fairly functional. So I said, all right, well, what's the first thing I have to do? Break it up into chunks of 2. Now, this is probably a little bit crazy looking at first if you don't read Swift. I'm declaring a function. The name of the function that I'm declaring is take2. It accepts 2 arguments, list and index of first character. These are just decoration, these are labels, so that when I call take2, I'll have to say take2 paren from, and then I'll give the first argument, and then starting at, and then I'll give the second argument. So they're external labels. They're very useful for writing functions that read fairly well, but they are very confusing to people who are not accustomed to being able to just decorate your function calls. The first thing that I'm going to accept is a character view of a string, which you might be a little bit confused by at first, but if you think about the many ways that you have to represent strings in Haskell, we are in a similar situation in Swift because we're trying to do Unicode correctly. So what that means is a string, you can't enumerate over a string, you can't iterate over a string, because they're like, well, you could be iterating over the UTF-8, UTF-16, per character and whatnot, so you have to actually specify like this. So I say, I want a character view, and then this is actually the interesting part, in my opinion, which is I accept an index of the character view, right? Like, where should I start taking 2 at? And then I will return a string and a cursor. And the string that I'm returning is the 2 characters that I bit off, basically. And the cursor is, just at the end of those 2 characters. So you can take the next 2 if you'd like. The first thing that I'm going to check is that I'm not at the end of the string. If I am at the end of the string, I'm going to return nil. Right? I'd explain the guard syntax, but you can just pull that from there. Then I say, all right, well, take a character. And one interesting thing to note is, I believe that this is close to like a Lisp, in that I'm not trying to say the thing at index 0. I'm saying give me the first thing in the list. And then I'm getting an index based on that and saying, well, if I'm now at the end of the list, then we can stop. So at no point do I care, like, do I assume that I have more? And using indices kind of helps me avoid having to worry about integers and whether or not I'm actually doing the right thing there. All right. After that, I say, okay, am I at the end of the list? I've already grabbed 1 character. I need to grab 1 more. And if I am at the end of the list, well then I can't grab another one. I'm going to return nil. We failed in our mission. But if I grab a second one, then I'm going to turn those 2 characters into a string and return the index that I'm at now. All of that is to say that this function, all it does is take 2 characters and return a string, or nil if it couldn't do that. Once I have that, I basically can do most of the work that I need to do now. I'm given a string, and I'm going to get the character view. Now that I have the character view, I'm going to say, well, is this character view an even number of characters long? If not, I have to pad the front of the string. Found that out at busconf. I hadn't thought about that because the one that I had was even length. Then I prime my output, and I very rarely write var, but sometimes it's the right thing to do. In Swift, reduce is not actually that great to use, because every time you create a new array, like if your reduce is creating an array, every pass of reduce is generating a brand new array. There's no efficiency there in terms of sort of growing an array or knowing what you're going to get to and saving space in any way like that. So what I tell people is, reduce is beautiful. Use reduce if you are more concerned with writing beautiful code, but the moment that performance becomes an issue, think about every place that you're using reduce, because that actually might be a performance problem. Now, once I have that, I'm doing a little whilelet, and what that is I'm saying, okay, take 2, and then keep taking 2 until this take 2 function returns nil. And again, this is just me avoiding reduce. And I decided to eagerly avoid reduce here because I can easily imagine someone giving me a very long string. But all of that said and done, everything else here is just converting those 2 characters into a number and then turning it into a code point in ASCII or Unicode and then making a string out of that array. And I'm not going to belabor that because we've already spent a good amount of time on this example. And this is just to show you that you can do non-trivial things in Swift using functional programming ideas where, just like we were saying, we've been saying a couple times, you want one function that does one thing fairly well. Right? But let's go to a slightly more canonical example that is used in terms of functional programming and the like. Apparently my folders have been alright, let's talk factorial. How many people know what factorial is? Right. I think maybe most people raise their hand. Does anyone need me to explain factorial? I don't like to ask it that way, but does anyone need me to explain factorial? Awesome. All right. So to compute factorial, if you're doing a for loop, there's not much to it if you know what factorial is. The first thing that I'm doing is I'm checking to make sure that I wasn't given a 0 or less. Because if I was, then factorial doesn't really work. And precondition is just going to crash. You could do something more graceful, I guess. But I like to punish people for terrible, terrible things. And then we start at 1, because that's multiplicative identity, and we just multiply going up. And it's so wonderful and great, except almost everyone who's explaining factorial will show you a graph immediately where they say, after you've calculated up through a number, why do you do it again? It's so wasteful. Okay, so how do we do that? Well, first we'll take a detour and say, I really dislike that for loop. Isn't there a way? Huh?
Hold on, quick question. Suppose you had accepted 0 for n, then what would happen if you looped from 1 to 0? Would it just do nothing, or?
Oh, if I'd looped from 1 to 0, I don't think it would. I think it would crash at runtime. Okay. Because creating a range where the end is less than the beginning is not really, it's frowned upon. Okay. Good question though, thank you. So again, I've just converted that for loop. And this does not have the same problem, in my opinion, as the reduce array situation that I talked about where you want to avoid that, because we're not creating a new data structure. Like, we need to create this value regardless, right? We need to create a new number every time, and we're not taking up more and more space in a fairly aggressive way. All right, now that I've gone and done that, what I'm really going to do is I'm going to take a step towards being able to memoize this function. To do that, I actually want an inner function. And fortunately, Swift, just like a Scala or a lot of other languages, allows you to just declare another function inside of the function that you're in. Right? So I have gone with the convention of a leading underscore, because that helps you know that this is not the function that other people should be seeing. This is just for my use. And I accept an integer. And if I'm at 1, I return 1. Awesome. Great. Which is confusing if you think about going through factorial the way a human normally would, which is multiply 1, multiply 2, multiply 3. But you can see here that we're actually counting down. And I don't have a lot of time, but I'm going to try to explain this as succinctly as possible, and stop me if I fail. What we're essentially doing is we're saying, if you ask me for factorial 4, I'm going to immediately start and say, all right, we'll go 4, get here, and say, well, 4 is not 1. And I'm going to say, all right, well, this is what you gave me, a 4. And I know that I have to multiply factorial of 3, which I don't know yet, by 4. Cool. What's factorial of 3? And then I'm going to do the same thing where I say, well, I know that factorial 3 is 3 times factorial 2, which I don't know yet. So let me just write down that I need to know what factorial 2 is, or 3 is, and then I do that until I get to 1. And then I basically have a list of things, a list of gaps that I have now filled. And now I can go backwards and say, all right, well, I was at 1, I know what 1 is. And oh, now that I have 1, I can do 2 times factorial of 1. Cool. And now that I have factorial of 2, oh, now I can do 3 times factorial of 2. And then we sort of have our answer.
So TJ, yesterday in the BusConf you were saying something about tail call recursion, right?
Yes.
Is this one of those cases where it can actually do it by itself?
Okay, so the question was, basically, is this tail call, is this eligible for tail call optimization? And it is, but what I was talking about on the bus, which was the leading part of the question, is that we're not guaranteed tail call optimization in Swift yet. Or in any, we're not guaranteed it, I shouldn't say yet. I've put in a little request in Swift Evolution, which is the mailing list where you can try to steer the language for a keyword or an attribute or a tag or something where we can say, I expect tail call optimization, and then you can just let the compiler tell you, I can do it or I can't. And if it can't, then you can try something else, and that's fine. But we don't have that yet. So basically, I say right now that we don't have tail call optimization. Write this kind of function at your own risk. I haven't had too many problems, but I also am not terribly performance-minded until a problem occurs. All right. So so now that I've done this, right? Because at first this does not seem like I've actually gained a lot in terms of. Oh, sorry, I have another question.
Quick and dirty tail call optimization.
I will have to talk about that later. I'm trying to actually end at 10. Cool. So the long and short of it is, because this function, I guess I'm going to answer it. The long and short of it is, because this function calls itself in tail call position, which is to say at the very end of the function, and the arguments fit some sort of shape, the compiler can say, well, I can actually sort of turn that into a loop which will be faster at, and like I can reshape this and the way that it actually compiles to make it not blow the stack, and to make it really stack efficient. I'm probably butchering that in terms of the details, but we're just trying to get through it. Now that I've done that, though, I can actually cache, right? Tail call optimization is a nice benefit for that factorial thing, but that doesn't get rid of the fact that if I do factorial 6 and then factorial 7, I'm going to compute all the way up through 1 through 6 that second time when I already knew the answers. So now what I'm going to do is I'm going to make a little cache, and I'm just going to make a cache. And let me actually change this name here because there's no need to do that anymore. And this cache is just going to be basically an int to int, right? A key value pair kind of situation, hash map or dictionary or whatever you call it in your language. And now that I have that, I'm going to say, well, for every time I get an input and create an output, I'm going to store that in my dictionary. Then I have to complicate my inner function just a little bit. Before I do the things that I used to do, right, which is just check for 1, figure out the one before it, or one less than, I say, well, do I already have the answer? And if I already have the answer, I just return it. That is great and wonderful, but right now this only works for ints. And I'm going to show you something. Well, we're going to come back to this. Sorry. All right. 28 minutes. Can we do it? Let's find out. All right. All right. So the other part of this, and maybe I should have started with this, but we'll see. The other part of this is talking about polymorphism and generics and whatnot, because you'll find that Swift is not a functional programming language in terms of its goals or what they're really trying to afford you. There were some useful and powerful techniques from functional programming that the Swift team wanted to take in. So filter, map, reduce, many ideas from functional programming are definitely in Swift. But overall, it is still primarily sort of a object-oriented or protocol-oriented language. Which means that you really, if you want to get into trying to do functional programming and using those techniques, really are going to have more bang for your buck leaning on the type system and all of the lessons that you can learn from strong types and having a good type checker that will just stop bad code from compiling for you. So to that end, we want to understand polymorphism, and there are three basic-ish, three groups of polymorphism: parametric, trait polymorphism, and ad hoc polymorphism. And I'm now going to speed through this. Unbounded parametric polymorphism is when we don't have any restriction on what kind of types we accept. Trait polymorphism is when we actually say, oh, well, I'll work for any equatable or any comparable or any hashable something or other. And then ad hoc is function overloading. Let's talk about that for a little bit more. And forced ignorance. So the reason that we like parametric polymorphism is we know nothing about the types that we are abstract over. So for any t, what does that mean? Well, arrays. Arrays are a great example of this because an array holds a list of things. and it knows nothing about the kind of thing that it holds. So an array of ints, the array itself knows nothing about integers. It just knows how to hold a bunch of them. And if I change that integer to be dictionary, I'm an array of dictionaries. Now, why is this useful? As I implement array, none of my methods will accidentally use something about integers. They can't. I can't call a method on element because in my mind, element has no behavior. You can use this on structs, you can use this on classes, you can use this on enumerations, which are ADTs, or algebraic data types in Swift. So our methods, our functions can also be generic in this way. So generic is the word that we use in Swift. So I can map over T, any T. I don't care. Yeah.
So I see that there's exceptions and stuff being thrown and rethrown. Does Swift have some types?
Some types.
Like either or something?
Yeah, so enums, ADTs, you can model some types with enums. And we don't, in the standard library, have like result or either. There are lots of reasons and debates, and we won't really go too much into that. The only reason I actually left throws and rethrows in here is because this is literally the signature in the standard library. Right? So if you went and looked right now, this should be what you actually encounter. And what we're saying here is map is a function or a method that is abstract over T, which means you can hand me any T. Doesn't matter. And when the time comes, I'll do the right thing. We're good. And array already has an element type. So what you're going to hand me is a closure that can go from array to T. And if you do that, I will give you an array of T. And most people know how this works. Under the covers, we're basically going to call for every element in our array. We're going to call the closure that you provided, convert that into a T, and we're done. Bob's your uncle. We can also do this for protocols, which are similar to Haskell type classes or Java interfaces. It's basically describing a contract or a set of behavior without having a concrete implementation. So you can say that I accept something that has some other type associated with it, element, and a method named next, which will return, oh, this question mark means optional or maybe. Right, so option in Scala, maybe in Haskell, that sort of thing. So it may or may not return an element. Right. So trait polymorphism is very much the same, except we know something about T. We don't know everything about T, but we know something. What do I mean? In Swift, sets don't use order like they do in Haskell. They use hash values. So hashable. In order to store something in a set, the element must be hashable because I want to ask for a hash value. And if we looked further into it, hashable extends equatable. So we also have equals. So with a hash value and an equals, we can implement set. And unfortunately, I don't have time to explain hash values. Dictionary uses the same mechanism, and we can tell that because keys must be hashable. And this is one of the first nice things about trait polymorphism. You can actually gain some insight into into what will happen based on what is required. Min and max are great examples of this. The generic min and max functions require your type to be comparable. I can assume that's because they're probably going to compare the values that you give it. Let's speed through this just a little bit. You also have function overloading. So long as the types and the labels don't match up exactly, you can write two functions with the same leading name and the same arity. An example of this is numeric cast. So if you're trying to mix integers and floats in terms of computations, that does not work, right? I can't multiply a float by an int, but this bit of overloading means that if you use numeric cast, which you should not, it exists and it's there, but don't do it. Okay. Really need to emphasize that. Don't actually use this eagerly. Don't be like, oh, I'm trying to multiply two things that aren't the same, let's just do it. No. All right. But what it is basically a little truth table. Unsigned integer type and signed integer type. Signed integer type, unsigned integer type. Unsigned integer type, unsigned integer type. Signed integer type, signed. All right. Well, yeah.
Is there no like wildcard, like the last value, the otherwise?
No.
Okay.
Well, there is, but so any is kind of the wild card, I guess. But then you don't know anything about any, right? So if you say,
a lot like me.
well, I'm saying like if I was multiplying an int by any, I actually can't really write that in any reasonable way because any means it could be anything. And I know absolutely nothing about it because it could be anything. It could have this behavior, but it probably doesn't. And so this only handles integers. You know, there's probably some other thing that you should not use here. But the point is that numeric cast, its type is basically, it's basically all of these overlaid with each other. You know, the effect of this is that I can call it with any two integer types. Any two unsigned integer types, or any unsigned integer type and signed. So I think I don't have to explain why we care about polymorphism, do I? Maybe. That's good. One of the main reasons that I actually like is enforced shape. So maybe people haven't thought about this. Part of the power of maybe or option comes from the fact that maybe for any type has basically the same shape, and I don't need to know anything about none. I don't need to know anything about anything to make a none of some type, like of t or int or whatever. I don't need to know anything about the thing that I'm abstract over. What do I mean? Well, if you think about the monadic operations, or sort of chaining these things where you say, well, if I don't have a number, there's nothing to do, and I'm just going to return none. That works because I can easily say I have nothing at any moment. It's kind of like if someone asks you for the answer to a hard question. Saying I don't know, super easy. Like painless, right? Doesn't matter the question. Go ahead, ask me a question. I don't know. Ask me a question. Don't know the answer to that. Ask me a question.
It's the capital of Angola.
Don't know the answer to that one, right? Like you can create I don't know without knowing anything. That's the point of it. That's none. The sum case, I actually know how to, I have to either have some value to put in the sum or know how to create some value to put in sum, right? So this is a big thing that I lean on in terms of using the types to help guide and delineate what do I know, what can I make, and is there a way that I can protect myself from being able to like generate a nonsense value. All right. So a big problem, in my opinion, is that every line, if you look in the standard library of this, is required. Even those comments, which is what most of this is. Because this isn't dependently typed. There's no way to guarantee that you implemented equals in a sane way, so you can do something like this. And that's totally legit, as the type suggests. Right? I can just randomly say, yeah, we're equal, or not right now. And I don't have the internet or whatever. There's supposed to be a funny little thing of something blowing up in the background because this is terrible. But it compiles and everything is fine. All right, so I've tried to go through that a little too quickly so that we could answer questions and I could show some reasonably interesting code as well. So first of all, how many people can read Swift to some extent?
Apparently.
Yeah, that's good. That's good. That's good. Right? And so that's why I skipped over the quick introduction, because we were going to go into advanced enough Swift that I couldn't like ramp up from nothing to generics.
So I have one real simple question. What's the underscore ahead of the
Aha.
argument there?
So that's a good question. So the question is, what's the underscore in front of this argument? So I said that if I put a word here, it'd be a label, but this underscore means I don't need any label. What do I mean? Let's just quickly say, let's say factorial n int return -1, because that's not the point. If I say factorial, for this to compile, I actually need the label here. But if I underscore there, it'll say you should get rid of that label. Come on, buddy. I believe in you. There you go. Right. So that's all that underscore is. Now that we've looked at some generic stuff, let's go crazy. Let's just go ham. All right? So before we do this, let's actually look at this this final form of our cached, our memoized factorial again. We have the inner function, which the very first thing that it does is just check for whether or not we've already done this. Well, I want to do this for all things, right? If my input is hashable, I should be able to memoize input and output so long as it's a pure function. Right? So long as my output is completely dependent on my input and nothing else. Well, here we go. This is me saying, all right, my input, I'm abstract over two things. My input has to be hashable. That's it. That's all I need to know about it. And my output, well, it can be anything. And I want you to hand me the body of the function. But we're actually doing something a little bit weird. For a more robust explanation of why we are accepting another closure with our same shape and a number, the Advanced Swift talk at WWDC 2013 is a more full explanation. But basically, if we're going to memoize, we end up with this moment where we need to refer to ourselves, but we are defining ourselves generically, and that becomes a problem, right? This whole inner function dance doesn't work because we're trying to do it generally. When I wrote a function with the name underscore factorial, it was like, that's cool. You can refer to underscore factorial, and that's clearly separate from factorial. But now that I'm trying to just handle all cases where my input is hashable, we get fancier. So I make a little dictionary here, and this dictionary is going to live on kind of for the lifetime of this closure that it returns. And what we're going to do is we're going to make basically a maybe of our body, of our function body. That exclamation point meant that I will always assume that it is valid whenever I try to reference it, because there should actually be no moment where I don't have a function body. So I'm going to elide all of the protection and syntax that would say, oh, well, this could be nil right now, so let's not, So then I actually immediately assign result, which is part of why I know that it's always valid. Well, what is it? Check for whether or not we have something in the cache. Right, so hand in the key, and if we have a value, if a value comes out, well then we can just return the value that comes out. That's what that if let is doing, and that's sort of do notation kind of syntactic sugar thing going on with an optional. So let's elaborate this just a little bit. This is checking for the output of memo subscript x and saying, if that's nil, well then we're not going to do the function body. If it isn't nil, then we have something, we're good. We have an answer, return it. Otherwise, execute the body.
Where's X coming from?
X. So this is a lambda, like this is a that I'm declaring right now. So it would probably be a little clearer to that, right? So result is a lambda. X is not int in. And it looks like I can't do that. All right. So, do we have questions about what we see here? Because this is not trivial. All right. So that's memorize. I'm going on, and I have to agree with Alejandro that you all need coffee or something. I'll make you do jumping jacks if you don't listen, or play a listening game. But another interesting example, in my opinion, is sets. So I just told you that sets require their elements to be hashable, which is not that bad, except for the fact that I don't know how to write a hash function, and this is not even me being facetious. I don't know how to write a good hash function. I often am like, that's good enough. Right? Because hashes are hard to write. How many people agree? Wow. So some people are like, I got that. That's easy. I need to talk to you later. All right. So for fun, I'm going to declare a protocol called setType. I'm going to say, oh, well, this is just a set, which is confusing, and this is why I had to say setType, because there is a type set, which accepts hashable, but I'm going to implement a set that only requires that its elements be comparable, kind of like Haskell. So I think, well, what's the bare minimum that a set needs? Well, you need to be able to create an empty set, you need to be able to insert something in the set, and then you need to be able to ask if an object is in the set, right? That's bare minimum. Do it, like, wake up. I will point at people individually. Okay.
Size of the set.
The size of the set actually would be good. Maybe we'll add that if we have a moment. Well, the first thing that I want to do is I want immediate results with like very little work. So I'm going to make set conform to set type. I'm going to add a method named inserting, and all I really have to do is make a set with one object, union it with self, and just return that thing. Cool. And then there's already a contains method. Awesome. Well, now that I've done that, let's actually see a less trivial situation where I do need to do some work. I still have set type, same thing, nothing's changed. But now I'm going to use Swift enums. And I probably should have just made this whole presentation about enums because they're delicious. This enum just has two cases. I'm either empty or I have an element and then two unbalanced sets on either side of that element.
Is this the equivalent of sum types?
Yes. Yes. This is the equivalent of sum types. That was the question, sorry. And I have to mark it as indirect because I have myself as an associated value. Right? So I have an unbalanced set in my unbalanced set, and that means that some memory layout stuff has to happen behind the scenes. Okay, so making it empty, fairly easy. Inserting becomes a little bit visually noisy, but this is why I love enums and switches. If I'm empty and I'm inserting an element, there's not a lot to do. I'm going to return a tree with empty on either side, because I just have one thing.
Is the dot keyword a string?
The dot here is just shorthand, so I don't have to write, oh wow, anything, because I can't type. It's just because I've already said that it's, oh wow, unbalanced set. I've already said here that those both are of type unbalanced set, so the compiler's like, well, you could just leave that off. I know that already. All right, so that's easy. Either side, empty, empty. And then we pick whether or not we add to the left side or the right side based on whether or not the object that you gave us is less than or greater than or equal to, I guess, whatever we have in our tree already. What do I mean? Well, if I'm not empty, then I say, all right, well, I need my left side, I need a node, and I need my right side. And this where is saying, we're only going to execute this code if element is less than node. Right? If the thing you gave me is less than the node that I'm looking at, then I'm going to add to the left side. I'm going to insert in the left side. And the idea here is that eventually I'll get to a node that's just one thing. And I'll end up comparing to an empty node. And I think you understand where this is going, yeah?
One thing that confuses me is that this is supposed to return self, right? Like, return itself. Like
it's self-type, yes.
Oh, self-type?
Yeah.
Are you mutating the set?
No. So I am not mutating myself, which honestly is not always the best way to go in Swift. Mutation is fast and the norm. But the question was, I'm returning self here, so does that mean that I'm mutating myself? And no. Everything that I'm doing in terms of this, this set implementation is from, oh wow, I don't remember his last name right now, but purely functional data structures.
Sure.
Osaki.
So that's my type, not my instance.
Right. So self is my type, not my instance, correct. And it's Chris Ozaki.
Okazaki.
Purely functional data types
So
is the name of the book.
Also, that inserting method also returns a new...
Yes, and if you look here, this insert method, this inserting method returns an unbalanced set of elements. Right? If I was not doing that, I would actually want to mark this as mutating. So you get a pretty good indicator of when you're mutating a value type. If you're working with classes, you don't have that mutating keyword appended there. So typically, if you really are going to try to write functional programming, someone has the book right there. So typically, if you are going to write functional programming style code, and you're really trying to adhere to no mutation, you're going to use value types, so enums or structs, and you're never going to write mutating. And then you're good. And then checking for whether or not something is a member is fairly easy. Well, if you gave me an element and I'm looking at an empty case, we're not equal. And if you gave me an element and I'm looking at a node that has less, less than, okay, all right, well, fine. If we're less than, obviously we're not equal. If we're greater than, obviously we're not equal. And because I've handled the less than and greater than cases, well, if it's a tree, we're equal. Right? I've pushed the other cases out of possibility. Right. All right, so that was sort of, yeah?
You skipped inserting the last case?
Inserting, so in inserting, I skipped the last case. Oh, because if we try to insert something where it's the same logic. So if we're not less than and we're not equal, or we're not greater than, we must be equal to. So there's actually no insertion to do because the node that I have is equal to the element that you gave me. So nothing changes about the structure. Thank you. I did miss that. Now, that was sort of a shotgun approach to functional programming in Swift. I tried to show as many different things as I could, but I know that I can't show them all. We have 4 minutes left. Are there any questions? Is there some burning desire of yours that you want answered? Oh, wow. He had his hand up first, then you, then you. Yep. You, yes, no, gray shirt.
Yeah. So I've noticed that you have to write a lot of this escaping and indirect and all of that. So is there a reason why sort of the Swift compiler decided that you have to mark all of this explicitly instead of like just as any other compiler does, just figuring out, well, if I'm using myself there, then I'm actually indirect?
Okay, so the question is, we have at escaping and at indirect, and is there any reason that the compiler doesn't just infer a lot of that for you? Why is the burden placed on the developer? And okay, so we're basically theoretically out of time. At escaping, at escaping, wow. I closed all the things that have at escaping. Factorial, there we go. There we go, at escaping. If I delete this, the compiler actually recognizes that I'm using this in a closure, and the closure that you've given me might outlive the function that we're in. So it'll tell me, and it'll even help me mark at escaping. Right, so I don't know why I almost pointed at the screen. At escaping, and then if I let it do the fix it just writes it for me. So we're sort of in the middle ground where the compiler does recognize it for you, but it wants you to explicitly mark it. And I think that that's an acceptable compromise, because if you decide that you don't want to mark it because you didn't want it to be escaping, now's your moment. Right? Like escaping has implications in terms of lifetime of objects, because automatic reference counting and closures are probably one of the only cases where you can create reference cycles very easily in Swift. And so marking something as at escaping has implications, and you should think about those before you actually add it.
So you don't have garbage collection in Swift?
No, no garbage collection in Swift. And there's a wonderful paper, or talk, with slides by Chris Slatner that happened a couple weeks ago, where he defends it and explains it. Garbage collection is not so great. It's hard to reason about. Arc is a wonderful compromise until that moment when you actually have to think about it and control it. And we're trying to get the last bits to ease that one case. There you go. You had a question.
This is a very general thing, and maybe like something we can talk about later. But I'm curious to hear what are some situations when you're developing apps where your style of writing code within the framework of UIKit has changed with using these principles.
So that is a broad question. So how has my style of writing code changed with regard to UIKit? The shortest answer that I can give you is I tend to write libraries that are basically pure Swift, and in the library itself you get to write kind of as beautifully as you want. You can do functional programming stuff. You don't have to constrain yourself by like object-oriented programming or anything like that. But then the moment that you start to interface with Cocoa and UIKit and all of the UI-related stuff, you realize that views are mutable state. Like they're just made up of mutable state, and so that's the moment that you have compromises and you have to actually start thinking about mutable state and using it. But the nice thing is, if you take that approach where you write just pure Swift, your layer where you're actually making those mutable decisions becomes very thin and very obvious. Right? Everything else is clearly immutable, or all that you have a great, clear moment where you're like, I'm doing this because of views.
So is like at least manual currying or partial application practical in this language?
Manual currying, practical. Depends on your definition of practical.
Well, obviously you can put functions inside functions, and so you could get.
Yeah. You can manually curry. It is definitely practical if that is how you think, right? In my opinion, it's not worth it for someone who doesn't already have some intuition about functional programming and currying and whatnot, and that's not to some degree natural to them, because you will end up manually writing a lot of arrows and having to keep track of how many layers of currying you want, and for things like tuples where technically you could have an infinite amount of currying, you're not going to write an infinite amount of currying. So some people have written little libraries where they've gone out to 23 arity for currying, and that's not so practical. But if you're making like a builder kind of pattern, and you want to say, oh well, if you just give me the name, I'll give you a closure back that expects the age and the height, and then that sort of thing. That's perfectly great and practical. All right, so we are out of time, but feel free to bother me, or let's use a different word. Feel free to approach me later on and ask any questions that you have, and I love talking about this, hopefully, as you've noticed.